Children, let's discuss about extrinsic semiconductor now. Extrinsic semiconductor is known as a doped semiconductor or a semiconductor with suitable impurity added to it. So we had studied that in intrinsic semiconductor, no impurities are added. It is the pure semiconductor. But a small amount of suitable impurity is added to a semiconductor so that it will conduct more electricity without supplying external energy. See, you might just recall the working of intrinsic semiconductor. There, we need to supply some external energy in order to increase the conductivity of intrinsic semiconductor. In the absence of external energy, it was an insulator. So here, in the absence of thermal energy itself, if we want to make a semiconductor as a conductor, we need to add some impurities in small amount. And this process of adding impurity to a semiconductor in order to increase the conductivity of that semiconductor is known as doping. And the impurity added semiconductor is known as doped semiconductor. Doped semiconductor. And impurities that are added is known as dopants. The added impurities are called dopants, and that semiconductor to which the impurity has been added is called doped semiconductor, and this process of adding impurity is called doping. There are two types of extrinsic semiconductor. First one is N-type and second one is P-type. So a detailed study of N-type and P-type semiconductors help us to understand better about the extrinsic semiconductor. So let's first discuss about N-type semiconductor. N-type semiconductor. So N-type or P-type, whatever it be, some amount of impurities are added. But the nature of impurities added to N-type and P-type will be different. That is the difference. Okay. So when pure silicon or germanium atom, which has 4 valence electrons, is doped with controlled amount of pentavalent atoms like arsenic, phosphorus, antimony or bismuth, we get an N-type semiconductor. So when will we get an N-type semiconductor? When this silicon or germanium atom is doped with pentavalent atoms. Pentavalent means what? Atoms having 5 electrons in their valence shell. Okay. So whenever arsenic, phosphorus, antimony or bismuth are added to a pure silicon or germanium semiconductor, N-type semiconductor is obtained. Okay. And how we can explain the working of N-type semiconductor? So for that, we need to consider the crystal structure again. So this is the pure germanium crystal structure, and to that pure germanium atom, an arsenic, that means a pentavalent impurity, we can add any pentavalent impurity. When arsenic atom is added, that arsenic atom can be considered as an impurity atom. So what happens? One of the germanium atom in the crystal lattice is replaced by the arsenic atom. Okay. Then, you know, arsenic atom has 5 valence electrons, that is 1, 2, 3, 4, 5. 5 valence electrons are there in an arsenic atom. But germanium atom, on the other hand, it has only 4 valence electrons. So what happens? 4 out of 5 valence electrons of the arsenic atom forms covalent bond with the neighboring germanium atoms. Okay, here you can see the 4 valence electrons of the arsenic atom form covalent bonds with the neighboring germanium atom. So 4 valence electrons of the arsenic atom are engaged now, but 1 electron is free, isn't it? Because arsenic has 5 valence electrons. So out of 5, 4 electrons engaged in bonding with the neighboring germanium atoms, and 1 valence electron is free. So that free electron will be available for conduction, and that electron is free to move through the crystal lattice. So whenever an electron is free, it will be available for conduction. It will conduct the current, isn't it? So when impurity atom arsenic is added to this pure semiconductor, a free electron is available for conduction, and that free electron will carry the current. Okay, again, if we supply external energy, so here in the absence of external energy itself, free electrons are available by the adding of impurities. And in addition to that, if we supply some external heat energy, what happens? The bond will break. The covalent bonds will break. When the covalent bonds break, more and more electrons will be free and they will be available for conduction. Again, when the covalent bond breaks, the previous scenario will repeat. Holes are formed, isn't it? Because when the covalent bond breaks, electrons will move from its position and it will be available for conduction. And when electrons move from the bond, a vacancy is created, which is the hole, and it is a positive charge. So as soon as a positive charge is created here, neighboring electron will be attracted to that positive center. So there again a hole is created. And as soon as this electron sees this positive center, it will be attracted to this hole. Again a hole is created. So the previous scenario repeats here. So here 3 types of electrons are produced. That means one electron, free electron, is available by the adding of impurities. And secondly, free electrons are available by the breaking of covalent bonds. And third, the electrons move from one hole to another hole. So here also electrons are available in 2 ways, by the adding of impurities and by the breaking of covalent bonds. So electrons are the majority carriers here. Holes are formed only due to the movement of electrons from one vacancy to another vacancy. So holes are the minority carriers and electrons are the majority carriers. So negatively charged electrons are the majority carriers in this type of semiconductor. Hence this semiconductor is known as N-type semiconductor. N stands for negatively charged, because negatively charged electrons are the majority carriers here, are dominant here. So this type of semiconductor is known as N-type semiconductor. And here number of electrons will be greater than number of holes. Okay. Then what are the examples? When arsenic, antimony, arsenic, antimony and also phosphorus, then bismuth are added to a silicon or germanium atom. The same procedure is when arsenic, phosphorus, antimony or bismuth are added to a germanium atom. What happens? Yes, an N-type semiconductor is obtained. And in N-type semiconductor, negatively charged electrons are the majority carriers. And in the in the energy band diagram, what happens? When a pentavalent impurity is added, an additional energy level is created here due to the impurity atom, and this additional energy level is known as donor energy state. Okay, so small temperature is needed for the electron to go to the conduction band. Okay, so this additional energy level is created just below the conduction band and it is known as the donor energy state. Again, due to the formation of this donor energy state, the energy gap is further reduced. So a small temperature is required for the electrons to move to the conduction band. Okay, so that's all about N-type semiconductor. Now what do you mean by P-type semiconductor? So P-type semiconductor is obtained whenever you add trivalent impurities like gallium, indium, boron or aluminium. Trivalent impurities means atoms with 3 valence electrons. So when pure silicon or germanium crystal is replaced, or which has 4 valence electrons, is doped with controlled amount of trivalent atoms like gallium, indium, boron or aluminium, we get a P-type semiconductor. So here you can see, to a germanium or silicon crystal, some amount of trivalent impurity such as boron is added. So what happens? When boron is added, one of the silicon atom is replaced by boron atom. And this boron atom has only 3 valence electrons. But this silicon atom has 4 valence electrons. Okay, here also there will be a valence electron. So what happens? This boron atom has a deficiency of 1 electron to form covalent bond with the neighboring silicon atom. So out of the 3 atoms, these 3 electrons of the boron atom forms covalent bond with the neighboring silicon atom. But here there is a deficiency of 1 electron to form covalent bond with this silicon atom. And deficiency of electron means hole, isn't it? So due to the addition of impurity atom, this trivalent impurity atom, a hole is created. We haven't supplied any external energy now. In the absence of external energy itself, hole is created. So as soon as hole is created here, electrons from the neighboring position will jump to this hole. So again a vacancy is created here. So due to that, electron from the neighboring position will jump to that hole. That means electron starts to move from one hole to another hole. So electron movement has taken place here in the absence of external energy itself, due to which some conductivity is observed in the P-type semiconductor. Now, in addition to that, if we supply external energy to this semiconductor, what happens? Covalent bonds will break and electrons will be available for conduction. Again, holes are created. So here holes are created by 2 ways. One, by the addition of impurity atom, trivalent impurity atom, and also second by the breaking of covalent bonds. But electrons are available only by one way, that is by the breaking of covalent bonds. So here electrons are the minority carriers and holes are the majority carriers. Okay, so holes are positively charged centers. Since positively charged holes are the majority carriers here, this type of extrinsic semiconductor is known as P-type semiconductor. So positively charged, hence the P stands for positively charged. Okay, so P-type semiconductor is obtained by adding trivalent impurities. Okay, and here positively charged holes are the majority carriers. So here we can write number of holes is greater than number of electrons in the case of P-type extrinsic semiconductor. So here you can write number of holes into number of electrons is equal to number of intrinsic carrier concentration square, Ni square. This is the condition that satisfies its equilibrium. Number of electrons into number of holes is equal to Ni square. Okay. And how can we explain using the energy band diagram? Here you can see when the trivalent impurity is added, an additional energy level is created just above the valence band, and this energy level is known as the acceptor energy level. Previously it was donor energy level because that pentavalent impurity atom donates 1 electron for the conduction. But here when the trivalent impurity atom is added, that trivalent atom accepts, a hole is created due to which it accepts the electrons. Okay, so that's why this energy level is known as acceptor energy level, and it is created just above the valence band. Again the energy gap is reduced and a small temperature is required for the electrons to move to the conduction band. Okay, so that's all about semiconductors, N-type and P-type semiconductors, and also intrinsic and extrinsic semiconductors. So intrinsic semiconductor is a pure semiconductor, and extrinsic semiconductor is the semiconductor in which we add some small amount of impurities. So 2 types of impurities can be added, trivalent impurity and a pentavalent impurity can be added. When a pentavalent impurity is added to the extrinsic semiconductor, N-type semiconductor is obtained. And when trivalent impurity is added to an extrinsic semiconductor, P-type semiconductor is obtained. And the conductivity of extrinsic semiconductor will be more than that of the intrinsic one. That means the purest one, because impurities have not been added in the intrinsic semiconductor to increase the conductivity. Okay. So with this, I am concluding this session. Notes of the topic and YouTube video have been uploaded. Please go through that. We will meet in the next session. Till then, take care all of you. Stay home, stay safe. Thank you.